Hello everyone. So in this video, we are going to see V curve, inverted V curve of synchronous generator and its application. Okay. So let's say you have this synchronous generator and it is connected to infinite bus bar, and infinite bus bar has characteristics like the terminal voltage or voltage at infinite bus bar will be constant, and frequency of infinite bus bar will also be constant. Okay. Now these are the assumptions and all. And if you write the KVL equation, you will get this equation, the internal induced EMF voltage equation of synchronous generator. Okay. Now, I want to know what is the V curve and inverted V curve. Actually, V curve is nothing but a plot in between armature current and field current, and inverted V curve is a plot in between power factor and field current. Okay. Now, let me proceed further. Let's say uh, your synchronous generator is connected to infinite bus bar, but there is no armature current. So if there is no armature current, from the equation number 1 you can see, if my Ia is equals to 0, then your EF and VT will be same. Okay, so these two are the same. That means EF and VT magnitude wise are same. Also the angle, if VT is at reference angle, my EF will be also at reference angle. So the scenario is something like that. You have this, let's say you have this terminal voltage or the bus bar voltage. It is my VT. My EF will be also be the same one. Okay. So my EF will be like this. So they are same in magnitude, so same in phase. So this is the condition. My EF and VT both are same, but my armature current is 0. Now tell me one thing. My field, this internal induced EMF, EF, or the terminal voltage at no load, you can say, EF is proportional to IF. Okay, because EF has, if you see the EF equations, EF is nothing but root 2 pi F, flux per pole, number of turns per phase, and kW, winding factor, and this flux per pole is directly proportional to field current. So that's why I'm writing EF is directly proportional to IF. Okay. Now even though there is no armature current, you still have this EF. Okay, so to set up this EF, you definitely need some kind of field current, right or wrong. We need definitely this to maintain this EF. We definitely need some non-zero value of IF. So let me draw that one. Let's say this is my graph. This is my armature current IA, and this is my IF. Okay, so at some IF here, at this IF, my EF and VT are same. Okay. Now let's say I want to check what will happen if my output power factor, or the power factor at this point, is purely lagging or purely leading. Okay. Now let me consider the first, that is purely lagging load condition. That means the load that is connected to generator terminal, it is purely lagging load. Let's say I want to say case 1 at 0 per unit active power delivery. 0 per unit active power delivery means the terminal current is making 90-degree angle with respect to voltage, or we can say the load is either purely capacitive or purely inductive. So at 0 per unit active power, there can be two cases. I can have ZPF lag load or ZPF lead load. So for example, I am considering ZPF lag. Now if you rearrange the KVL equation number 1, so you will get EF minus VT by JXS. Now at 0 per unit active power delivery, what will happen? At 0 per unit active power delivery means, you have two buses, let's say V1 at an angle of delta and V2 at an angle of 0 and X. So if the active power delivery between two buses are 0, then you can comment like this: V1 V2 by X sine delta is 0 and delta is 0. So my delta is 0. So from this particular observation, I can also say, since my Vt is at reference, so it is my 0, my EF will also be at 0 phase. Okay, because there is no active power delivery, 0 per unit active power, J excess. Okay, so if you calculate further, you will get EF minus Vt by excess minus 90 degree. So Ia is equals to EF excess minus Vt by excess minus 90 degree. Okay, so let me erase this thing also. Now, as we have seen in the previous slide, like EF is directly proportional to IF. Okay, so this EF I can replace by some, maybe EF is equals to K times of IF. Okay, so K times of IF and XS minus VT XS angle minus 90. Okay, so I am interested only in magnitude, let's say. So mod Ia is equals to K by XS, some I'm calling it as a M, another constant IF, minus it is something like, let's say, constant C. So if you see this equation number 2, it is a linear equation, MF minus C. So if I try to draw this particular equation, you will see I will be getting a linear equation after this. Okay, so this is my for ZPF lag. Why ZPF lag it is? If you see this particular equation, you have phase angle as minus 90 degrees. So it is purely lagging load, you can say. So it is pretty clear. It is a linear equation with positive slope. And after this point, if you increase the field current, your armature current will also increase like this linearly. Now let me consider the ZPF lead load. Sorry, ZPF lead load. I have the operating equation EF VT J IA XS. IA is equals to EF minus VT J XS. Okay. Now, basically from this point, if you decrease your IF, your EF will also decrease. Okay. Agree with me? Your EF, because if you are moving in this direction, backward direction, your EF will also decrease. And if your EF decreases, see, if your EF decreases from this phasor diagram also you can see, if your, let's say, you are decreasing your IF, so your EF will be like this. Your EF will be like this. And to get this particular EF, your current must be leading in nature. So this will be your IA such that if you get VT, and this will be your JIAXS waveform, JIAXS vector, you can say JIAXS vector. So if you add VT plus JIAXS, you will get this EF. Okay, so the moment you are decreasing your you can say the field current, your armature current will increase. Okay, in that case we will see how it will happen, but it is clear, right? If you decrease the IF, your EF will also decrease. Now if you see this particular term, if you decrease EF, this particular term will be simply negative. Now let me arrange it in that, in such a way, like I have taken out the minus common, VT minus EF by XS at an angle of 90, just rearrangement. And this is my EF, and initially this EF and my EF minus VT quantity was becoming negative. Now if you just remove the minus for time being, and if you calculate this value and then put minus sign, it will be the same scenario, just a rearrangement you can say. And why I have taken, why I did not take the phasor, because these are the same phasor, EF and VT, these are the same phasor, so there will be 0 degree only. Now IA, this minus 1 I can consider as a 180-degree angle. So VT minus EF, 180-degree angle by XS, 90 degree. So IA prime, IA bar, VT XS minus EF XS at an angle of 90 degree. See here, your current angle is leading 90 plus 90 degree. That means it is purely capacitive. Now let me put the same things like EF is equals to some constant K into IF. Okay, so I bar IA phasor is equals to BT by XS. I'm calling it as some constant, maybe C prime, minus some slope, maybe this time MF IF, and this is my angle. Now let me take the magnitude only, C bar minus M bar IF. If you see this particular equation 3, it is a linear equation with slope negative minus M. So as you increase IF, let's say from 0 to here, your IA will increase. Or you can also say like that way, if you decreasing your EF from this point, your IA will increase. Both are correct. So yeah, so this will be your ZPF lead. Why this is positive negative slope? It is because of this equations minus M bar. Okay, and what I have done here, I have assumed my EF is equal to some constant K with IF. So this is my linear equations, you can say, that I have assumed. So I just if you just put it, you will get some kind of linear equations. So that's how I got this equation number 3. Okay, so this is how you got V curve for 0 per unit active power delivery. So it is for 0 per unit active power delivery. Now let's say my synchronous generator is delivering 0.25 per unit active power. Okay, so we'll see what will happen in that case. Case case 2, like 0.25 per unit active power delivery. Now for that, again, let's say in synchronous machine or synchronous generator, when it is delivering 0.25 per unit active power, it can also operate as a overexcited machine. It can also operate as a underexcited machine. So let's say at 0.25 per unit active power, my synchronous generator is operating at unity power factor. If it is operating at unity power factor, if this is my terminal voltage VT and this is my armature current IA, this is my VT, which is constant basically, you will get your VT, and this will be your uh, JIXS, okay, and this will be your EF. Now tell me one thing, this particular EF value has definitely more magnitude than this VT. If you draw a circle, you will see the radius because of the EF circle will be much more than the radius of the circle VT. So for active power delivery of 0.25 per unit, you will be getting EF which is more than VT, even if your synchronous generator is operating at unity power factor. So if I try to show in this particular graph itself, uh, at unity power factor, you have IF, which is more than the previous case, more than the like 0 per unit case. So maybe you will getting the IF here, somewhere here, and for that IF, if you see here, for that particular IF, you are getting EF, and that EF is asking for this much amount of armature current. So your IF also increased, your IA also increase. So maybe this will be your the point, you can say. So what will happen? Uh, this particular point will move to this point for 0 per unit, 0.25 per unit active power delivery. Why? Because you have seen for unity power factor and 0.25 per unit active power delivery, you need more IF and you need more IA also from the previous 0 per unit active power case. So this point, initial 0 point, you can say it will shift to here. Now you have to check what will happen to the mm, uh, equations and all. Okay, and this is my, you can say, rotor angle or power angle. So if you see now you have non-zero power angle or rotor angle, whatever you want. So EF at an delta equal to VT at an 0 plus J IA XS. Now here you have this delta term, and delta term becoming, because of delta you are getting non-linear equation. So you cannot solve such type of linear equation. But the bottom line is same. Actually, the nature will be almost this only, but the curve that you will get, that will be not in linear nature, you can say. So maybe you will get the curve something like this. Okay, this is how you will get. And again, this is for 0.25 per unit active power delivery. If you increase the current, if you increase the load, again you need more IF, you need more IS. So yeah, this the 0 point or the sharp point will shift here, and you will get like this. You can say likewise you will get. So it is for 0.5 per unit active power delivery. Same thing you will get for 0.75 per unit. Again you will get for the 1 per unit. It is for 0.75 per unit. It will be for 1 per unit active power delivery. And these are the points, you can say, where you need minimum armature current. And luckily these are the points we call it as a uh, operating power factor as unity, you can say. And at unity power factor you need minimum armature current for, even if you go for from 0 per unit active power to 1 per unit active power. Why at unity power factor you need less armature current? We can see from this particular figure. Let's say your active power delivery is constant. Your active power delivery is constant. That means I can say, if I have this thing EF VT by XS sine delta is constant, this is nothing but active power. My terminal voltage of infinite busbar is constant, XS is constant. So my EF sine delta must be constant. For a constant active power delivery, if you want to change the operating power factor of a synchronous machine, so this particular condition has to be satisfied. And one more condition, from the terminal point of view, I have this 3 VT IA cos theta is equals to constant. This is the active power, right? Terminal voltage is constant, 3 is anyway constant, so my IA cos theta needs to be constant for constant active power delivery. And you can say for various power factor, this particular thing, this two thing has to be constant. Now observe carefully, this particular component is basically IA cos theta component. Why it is IA cos theta? Just assume this was your armature current, let's say IA1, and this was theta. What will be the IA cos theta? Obviously it is this component only. This is my IA cos theta. That's why I'm showing Even if the active power delivery is constant, but your operating power factor is changing, so this particular thing needs to be constant. Okay, so let me erase these things now. And also my EF sine delta needs to be constant, and EF sine delta is nothing but this value. This is the EF sine delta value. Okay, so your curve, your EF sine delta must lie here, your IA cos theta must lie here. Okay, now let's say at any operating point, due to some reason, let's say I want to change the operating power factor and all, and my IF EF sine delta or my EF has increased to this. Okay, if your EF increased to this, let's say it is EF2, in that case what will happen, your delta will decrease, and that can only happen if you increase the field excitation of synchronous generator. And this is also obvious, like if you increase the field excitation, your strength between magnetic rotating field and the rotor will be strong, so your delta will decrease, so this will be your delta 2. And your Vt and also EF2 will be Vt plus J I IA2 XS. So if you show this particular equation, you have now this is your IA XS, this is basically your J IA2 XS, and IA armature current will be simply perpendicular to this, right? So it will be here IA2, and this will be your operating power factor angle theta 2. So you can see if you increase the terminal, if you increase the field excitation, or if you increase the EF, your IA or armature current will also increase. So you can see here, like at unity power factor, you need minimum armature current, and as you move towards the right side, you can say your field excitation is increasing. That means you are delivering reactive power. So it is a lagging power factor region, and it is leading power factor region. Okay. Now if I draw the inverted V curve, IF, this is my power factor. So at 0 per unit active power, let's say this was your curve. Actually, for 0 per unit active power, we should not say, because we should not even draw the inverted V curve, because at 0 per unit active power, either my you can say either my operating power factor will be purely lagging or purely leading. So let me not to draw the power factor for 0 per unit active power delivery. Rather, I can draw for 0.25 per unit active power delivery. So here this will be the maximum power factor, that is unity. As I move further, as I move further, operating power factor will be lagging in nature, so it will be like this. So it is here in one the operating power factor. As I move further, my operating power factor will move from 1 to 0.95, from 0.9, so it will decrease. And same will happen at the left side also, it will be leading in nature. And this is for, let's say, point for point point 0.5 active power delivery, and let's say this will be your uh, this will be your for 0.05 per unit active power delivery. So this is how your B and inverted V curve will look like. And this is basically, it is very important from industry point of view. Why it is important, and we will see the what is the application in practical life. Okay, let's say you have a large network, and you did the powerful analysis, and you got to know that the generator that you have, let's say you have one generator bus, and it is connected to bus number, let's say 4. Okay, it is a generator bus, okay, PV bus. And after load flow solution, you got to know that your generator needs to deliver some P amount of active power and Q amount of reactive power, and you will also get the terminal voltage, and you will get the this bus voltage and the bus voltage angle. The load flow solution will give all of these things. What is the active power generation? What will be the reactive power generation for this particular generator? Now, once you have the data of this V curve and inverted V curve, and also you know that how much amount of active and reactive power you have to deliver. You can basically from this inverted V curve and V curve you can adjust your field current such that you can fulfill the load demand. Obviously the active power should come from the mechanical side, but by adjusting the field current you can fulfill the P demand and Q demand also. Obviously P demand will come from the mechanical side, that is you can say kind of you don't have any control, but to deliver, let's say you have to deliver this much amount of reactive power, then you have to adjust the field current. For example, let's say after load flow solution and all, you got to know that your generator needs to deliver 0.5 per unit active power, and let's say maybe 0.2 per unit reactive power. These are the two things that your generator needs to provide. Okay, now where is my generator zero point 0.5 active power curve? This one, the green one, is for 0.5 per unit active power curve. Okay, so now I have I have to deliver 0.5 per unit active power and 0.2 per unit reactive power. Now to deliver that active power reactive power, I have this graphs, you can say the from the power factor graph or inverted V curve graph, I will know what is the operating power factor this generator is having now, and according to my requirement I can adjust the field current. Let's say here my field current, maybe it will be somewhere here, so my field current must be this to fulfill the load demand. So you can say this V curve and inverted V curve is required for a power system operation point of view, also real time operations. So it is very important. And if still if you have any doubt regarding this concept, you can ask me in chat box. Thank you.